Hello and welcome everyone, and in this short video we will be discussing how to design a tension members. See, there are two types of problem. One is the analysis problem and other is design problem. In analysis problem we are given all the details of the structural member and we have to calculate and analyze the design strength of that member. Whereas in case of design problem we are given with the external working load, or we may have to change that into the factored load, and for that value of factored load we have to design a structural member which can have sufficient strength to resist that much value of factored load. So the following design procedure is adopted in case of tension members. First of all, we have to decide which type of section we are going to use. Maybe we can use channel sections, maybe we can use single angle sections or double angle sections like T around a gusset plate, and which section exactly we have to choose is decided by the cross sectional area of the gross section. So the gross area is calculated and this formula is TU divided by Fy by gamma mo. Now from where does it came? We know the formula for TDG, and TDG is equal to gross area into Fy by gamma mo, where gamma mo is equal to 1.1, and from here we can derive this formula. Okay, we calculate first of all the gross area. Okay, so this is gross area calculated to carry out the calculation of gross area for the selection of section, and in this case we are considering the yielding of the gross strength, because major portion of the tension member are susceptible to fail in yielding only. Okay, so here Tu is the factored tensile force. Okay, this is not the working tensile force, it is equal to working tensile force into 1.5. From this value of Ag calculated, now we have to select the suitable shape of section, which angle section, ISA, which section I have to use depending upon the type of a structure and the location of the member, such that gross area is 25 to 40% more than gross area calculated if this value of gross area comes out to be 100 centimeter square. Then I have to choose a section from the steel tables which have a gross area equal to 125 to 140 centimeter square. Alright. Then I have to decide which kind of connection I want to do in tension members. If I want a bolted connection, then I have to decide the grades of bolts and number of bolts required. And if I am going for the welded connection, then I have to fix the size of weld and the effective length of the weld. Okay. After doing this, I have to check the strength of the connections that we have designed, and that check will be done when we satisfy all these three strength values, and all these three values must be less than the design strength. So we check for TDG, TDN and TDV. Alright. After doing this check, at the last the IS 800 also suggests us the check for slenderness ratio of tension members. Now slenderness ratio will be cleared when I will be discussing in the compression member portion, that will be clear. But here table 5.1 gives us the maximum value of effective slenderness ratio, and you can just have the checks from this table, and it has a limiting maximum value of slenderness ratio L by R. L is the effective length of the member and R is the radius of gyration. And in this row it says that a tension member in which there is reversal of direct stresses due to loads other than wind or seismic forces. So for that maximum L by R should be 180. And next row it says a member normally acting as a tie in a roof truss or a bracing not considered effective when subjected to possible reversal of stresses into compression resulting from the action of wind or earthquake forces. So in that case maximum L by R by ratio is 350. See, what is this reversal of stresses? What happens in wind load? Sometime wind load is acting this way, sometime wind load is acting this way. Okay. Similar is the earthquake. They also act both sideways. Okay. So in that case, what happens in the members? The same member acts in one direction, it acts like a tension member, whereas in other direction it acts like a compression member. As such, in tension member we do not check for the slenderness ratio. But what happens due to reversal of stresses from tension member to compression member? So for that we check the slenderness ratio limits also, because you will see in the next unit, that is the compression member, that the value of slenderness ratio is critical in the design of compression members. So that's why we are checking here for the maximum L by R value also. So we will do a small example, and here we are being asked to design a single angle section for a tension member of a roof truss to carry a factor tensile force of 2 to 5 kilonewton. So here the factor tensile force is given. So we need not to multiply it separately with 1.5 as we do in the working loads. And the member is also subjected to possible reversal of stresses due to action of wind. So here we have to apply the maximum L by R value equal to 350, okay, because this is due to reversal of stresses into compression resulting from action of winds or earthquake forces. And this table 5.1 is actually given in IS 800. Alright, it says us to use a effective length of member which is equal to 3 meter and use M20 sock bolts of grade 4.6 for the connection. So here bolted connection is being used. Now let us first of all calculate the gross sectional area for the section. Now if we consider the yielding of the gross section, so from that AG will be equal to TU divided by Fy divided by 1.1. So same thing is done here, and we have got the gross area for the section equal to 990 millimeter square. And we have to go for a section which has almost gross sectional area 25 to 40% more than this calculated value. So that's why from the steel table we have chosen Indian standard angle 100 into 75. So this is unequal angle of thickness 8 mm which has a gross area 1336 millimeter square. Okay, and we can also check how to calculate the gross area of angle section, that we have also discussed. Now how many bolts do we have to provide? Since we are using M20 bolts with bolt hole diameter equal to 22 mm, and if we use gusset plate of thickness 10 mm, because there is one angle section and angle section is always connected with a gusset plate. So in case of bolt we have to calculate the strength first of all in case of single shear. So this is the formula, and there is only one shear plane, and that we have considered in the thread portion, considering the net sectional area in the threaded region, and this we have done, and it is equal to 45.272 kilonewton. And if we adopt the edge distance 40 mm and pitch 60 mm, then the strength of bolt in bearing will be calculated using this formula. And here first of all we have to calculate the value of Kb, and Kb is the smaller of all these four values. So we see that this becomes the value of Kb, and this is also used here. So when we do all these calculation, we get this value of bearing strength of bolt. And if we take the minimum of shear strength and bearing strength, so we see that one bolt has got this much strength. Okay, this is the minimum of bearing and shearing strength. So how many bolts are required to carry 225 kilonewton? We just have to divide the total factored tensile force acting on the tension member divided by the strength of one bolt, and this is rounded off to the 5 number of bolts. So here we are going to use 5 bolts. Okay, so this is the diagram of the angle section, and here if you see, all the details are also shown. Edge distance is shown, pitch is equal to, here 60 mm is taken. Okay, 60 mm pitch, and there are 5 bolts being used, and length of end connection is the distance between outermost bolts, and LC will be equal to 240 mm here, and this is our end distance, and 100 mm leg is connected here. Okay, that's why we have made holes in the leg which has a leg length of 100 mm. So the 75 mm leg will become the outstanding leg. So this will be helpful in calculation of shear lag width, and thickness of angle section is 8 mm. So let us calculate first of all strength against yielding, and this is TDG is equal to AGF by gamma MO, and here we have used the gross sectional area, and this is equal to 303.6 kilonewton, and this is obviously greater than the external factored tensile load that is coming, which is 225 kilonewton. Okay, so this check is valid. Okay, now let us check the strength of our connection in case of rupture of net section. So first of all we have to calculate the value of beta, and here beta involves the use of the value of outstanding leg length and BS. So outstanding leg length is 75 mm, thickness of plate is 8 mm, and this is the shear lag width 75 plus 40 minus 8, and this is the length of end connection LC, and from here we get the value of beta is equal to 1.206. Okay, now we have to calculate the value of TDN, and for that we have to calculate the value of ANC and AGO, and ANC can be calculated as the net area of connected leg. So 100 mm is the leg length of connected leg, and 22 mm is the diameter of bolt holes, and minus 8 by 2 due to rounding, and multiplied by thickness of the angle section. Okay, similarly we calculated AGO, and using all these value in the formula of TDN, we can get the value of TDN equal to 330 kilonewton. Now this is also greater than 225 kilonewton, so this is also valid in this case. Now the last strength that we need to check is the strength against block shear failure, and in block shear failure we have to draw the diagram of the blocks being sheared out, and here we have used 5 bolts, so it will be looking like this with 4 intermediate bolts and 1 corner bolts. Okay, so here this edge which you are seeing is the end of the plate, and this is also the end of the angle section, so there will be no internal forces developing on these two sides, but here internal forces will be of nature shear, and they will be parallel to the shear plane, and on this plane there will be forces perpendicular to the plane, so this is a tensile plane, and all the dimensions are also given here, and this is 40 and this is 240. From the diagram it is given already, and diameter of hole D0 is 22 mm. This also will be useful. Length of block here is 60 mm. This is because it is equal to 100 minus 40. Okay, because 40 is the distance of bolts from the outstanding leg. Okay, an outstanding leg will not be sheared out, because this is the block which is getting sheared. So this much length is equal to 100 minus 40, which is equal to 60 mm. All right, so the same thing is done here. Now we can calculate AVG value, and value of AVG, gross area of shear plane will be equal to the entire length of shear plane is 40 plus 240 and multiplied with the thickness of plate. Okay, and the value of ATG is equal to 100 minus 40 into 8. Okay, so the diagram of block being sheared out is very important, and then you can calculate the value of gross and net area very easily. Similarly, the net area of shear plane will be equal to 40 plus 240 minus 4.5 into 22, and there are 4 intermediate bolts and 1 corner bolts. Similarly, the net area of tensile plane will be equal to 100 minus 40 minus, since there is only 1 corner bolt, so we just have done 0.5 into 22, and this is multiplied with thickness of plate. And all these 4 areas are calculated and used in the 2 formulas of TDB, and finally we have taken the minimum of these 2 values, which is equal to 355 kilonewton, and this also is greater than the external factored load coming on the member, which is 225 kilonewton. So the tensile member that we have designed in this case is satisfying the external factored load sufficiently in all the 3 possible cases. Now at the end, we would also like to go for checking the maximum L by R or the slenderness ratio, and this is because of the reversal of stresses due to wind loads. And here the length of member is already given 3 meter. Now from where do we get the value of R? R is the radius of gyration. Now here we are going to check the maximum value of L by R. So maximum value of L by R will occur when we use the minimum value of radius of gyration, because radius of gyration is in denominator. So here we have to use minimum value of radius of gyration so that we can get a maximum value of L by R. Okay, so minimum value of radius of gyration is obtained from steel table only, because in a steel table there are radius of gyration also given along both the axis XX and YY axis, and whichever is minimum of these 2 is used here, and in this case we have got this value from the steel table 12.7, and this is used, and this is absolutely less than 350, which is the limit being put by the IS code. So this is how the design of tension member is being done. Of course, design is complex than the analysis, but it's not very difficult. Okay, and in course of design of tension members, we also use different elements like gusset plate, lug angles and tension splices. So what are these elements which we also use as a subsidiary element in tension members? So let us discuss each one of them, and the first one is gusset plate. Now we have already used this term many a times, and we are well familiar with gusset plate, and this is mostly used with the angle sections. So the gusset plate serves as both a method of joining the steel together for connecting beams and girders to columns, and of adding strength and support to each joint. Okay, so they serve 2 purposes. One is the joining of steel members together, and also they increases the strength and support at the joints. And we usually see these type of structures at railway stations under the foot over bridges. So you see this diagram clearly, and here this is the gusset plate, and at gusset plate how many members are connected? This one is the first member, second member, third member, fourth member. So the 4 members of this truss is being connected at one gusset plate. Similarly, you can count how many gusset plates are there on this truss. You can see this one is the topmost gusset plate, 1, 2. Okay, now on each side there are equal number of gusset plate, and we can count it has 1, 2, 3, 4, 5. So 5 on left, 5 on right, total is 10, and 2 on the mid. So there are total 12 gusset plate being used in this case of truss. So the next type of member is the lug angle. Now lug angle is a short length of angle section and it is normally attached to the main tension members at the connecting end. You can see in the diagram also, if this is my main tension members, then what happens in some cases, the length of end connection is the distance between outermost bolt, that is not sufficiently provided because of limitations. If our gusset plate is short or the place is not much available and our requirement of length of end connection is really large, then in that case we can shorten our length of end connection by providing a small length of angle section, and this is called lug angle. And of course in case of angles we can use only one lug angle. But if we have a channel section and the channel section have flanges at the top and bottoms, so we can use lug angle at the top also and lug angle at the bottom also. So few advantages of lug angle is that when a tension member is connected to a gusset plate at its end, a large number of bolts are required, especially when the tensile load is large, necessitating the provision of big size of gusset plate. So how can we reduce the size of gusset plate and the joint also? So this is done by provision of lug angle, and it also increases the efficiency of the outstanding leg, the leg which is not connected in the joint, and to decrease the length of the end connections. Okay. So how IS 800 view lug angles? They view it with effective connection of the lug angle which terminate at the end of the member, and the connection of the main tensile member with the lug angle start in advance of the member of the gusset plate. Okay. And minimum of 2 bolts or rivets or equivalent welds has to be provided if we are going to use lug angles. Alright. But nowadays lug angles are not much preferred, because it leads to development of eccentric connection, and in eccentric connection there is unnecessary development of bending moments, and also there is development of non-uniform stress distribution. So what happens, stresses start accumulating at the joints, and due to which stress concentration really increases and there is chances of failure at the joints. Okay. So this is not much preferred, but many a time it is used. Okay. Now the third type of subsidiary member that is used in connecting tension member is tension splice. So splice means connecting two members. So when we go for connection of two tensile members or a splicing of tensile members, there are chances that the available length is less in case of tension members, or the tension members have different thicknesses. So in those cases we use tension splices, and this is the diagram of tension splices being done in the web portion. Okay, and you can see the 3D view of web splicing. Okay, so in this case the first tensile member is connected with the second tensile member and both have a I section, and in this case a splicing is done in the web portion. So that's why it is called web splice. Whereas if we do splicing on the flange portion, so it is called flange splice. Okay, and this is my first and second I section subjected to tensile forces, and you can see this real life picture of two tensile members having I section, and they are being flange spliced and web spliced both. Okay. So in tension splice, both the sides of the member act as a cover plate to form a butt joint. Okay, and here bolts are placed to transfer the load, and if the tensile members are of different thicknesses, then we also use the filler plates or packing plates, and in such case we have discussed the use of reduction factor beta pk. Okay, so the strength of splice plate and bolts is called the design load, and design shear capacity of bolts carrying shear through packing plates in excess of 6 mm is reduced by incorporating this reduction factor beta pk, which we have discussed. Just like tension members are designed, similarly lug angles and tension splice are also designed. That which type of angle section I have to use as a lug angle, and how many bolts do I have to provide in tension splices. All these things are calculated and done just like we have done different numericals so far. And now we will move our discussion to next type of member, that is the connection member, from the next videos. So till that, stay tuned and stay safe. Thank you.